Hi, welcome back. In this video, we're going to use the definition of the definite integral to evaluate the definite integral from 0 to 2 of x squared minus x dx. So first of all, let's remind ourselves what the definition is. The definition of this definite integral is the limit as n approaches infinity of the Riemann sum. And the Riemann sum is a sum from 1 to n of f of xi times delta x. Well, xi is just some representative point of the ith subinterval. So I'm going to use the right endpoints of the subintervals. So it's f of xi is xi squared minus xi, and it's times delta x. So this is the definition. And so what we need to do is get everything in terms of i's and n's. All right, so let's first find delta x. Delta x is always b minus a over n. So in this case, it's 2 minus 0 over n, or 2 over n. Now let's visualize our endpoints. I'm going to use the right endpoints of this interval, of the subintervals that I'm going to get. So first of all, x0 is always the first endpoint of the big interval. And then to get x1, I move over to the right a distance of delta x. So x1 is there. And then to get x2, I move over another delta x. To get x3, I go another distance of delta x. And I keep going till I get xn minus 1. And then the last one, I go over delta x to get x sub n, which is supposed to be our last endpoint, in this case 2. So let's see what those endpoints are in terms of I and n. So let's list all our right endpoints. So x1 is my first right endpoint of my first subinterval. That was 0 plus a distance of delta x. So it's just going to be 2 over n. Then my second right endpoint was 0 plus 2 delta x's. So 2 times 2 over n. So that's x2. And then my third right endpoint, I go 0 plus 3 distances of delta x. So it's 3 times 2 over n. And I'm keeping it factored so I can see the pattern. So now I can see what xi has to be. Xi has to be I times 2 over n. And then I just want to check to make sure my xn turns out to be 2, if my pattern was correct. So xn should be n times delta x. And n times 2 over n is definitely 2. So that worked. So now let's set up the Riemann sum. So the Riemann sum is that sum from 1 to n of xi squared minus xi times delta x. Using I times 2 over n as my xi, I get the sum from 1 to n of I times 2 over n squared minus I times 2 over n. That's xi squared minus xi. And then multiply that by delta x, which is 2 over n. All right, so that's the Riemann sum, but now I have to take the limit of that Riemann sum as n goes to infinity. So let's write that out. So my definite integral is going to be the limit as n approaches infinity of that Riemann sum. I goes from 1 to n of I times 2 over n squared minus I times 2 over n, all of that times 2 over n. All right, so now let's start simplifying the sum. So I have to write limit each time. So I'm going to square the I times 2 over n. So when I do that, I get I squared times 4 over n squared. And then I still have an I times 2 over n. All of that is still being multiplied by 2 over n. So now I'm going to distribute the 2 over n into both terms. So I still have limit n approaches infinity, sum from 1 to n, I squared times, now I'm going to have an 8 over n to the third, minus I times 4 over n squared. I just distributed the 2 over n. And now I can break this up into two sums. So it's the limit as n approaches infinity of the first sum from 1 to n of I squared times 8 over n to the third, minus the second sum from 1 to n of I times 4 over n squared. Look at the first sum. The first sum, I squared times 8 over n to the third. Each term has an 8 over n to the third in it, and there's no I in that factor. So that means I can just bring that out using the distributive property. So I'm going to pull the 8 over n to the third out. So I'm left with the sum from 1 to n of I squared. And then the same thing in the second sum. The 4 over n squared, that has no I in it. So each term has a 4 over n squared in it that can be pulled out using distributive property. So pull the 4 over n squared out, and you're left with I goes from 1 to n of just I. All right, so now I have the sum of the first n, the sum of the squares of the first n positive integers. That's the first sum. And the second sum is just the sum of the first n positive integers. So that one will take Gauss's formula. The first one will take another formula. So I've got the limit, n approaches infinity, 8 over n to the third. And now I'm going to use the formula for the sum of the squares of the first n positive integers. That formula is n times n plus 1 times 2n plus 1 all over 6. The other one is Gauss's formula. That one is n times n plus 1 all over 2. All right, so now I can take the limit. So notice a few things cancel. If you divide in the first term, divide top and bottom by n to the third and simplify a little bit, the first one goes to 8 over 3. The second one, divide top and bottom by n squared, and 4 divided by 2 is 2. So that one you just get 2 for the limit. And so our final answer is 2/3. So that's the definite integral from 0 to 2 of x squared minus x dx using the definition of the definite integral. So what did we just do? So let's look at a picture of what we just did. So if we graph x squared minus x squared minus x is a parabola. The vertex is at 1/2, -1/4. So there's the graph of x squared minus x just from 0 to 2. And when we computed the definite integral from 0 to 2, what we computed was the net signed area. So there's the first region, A1, which is strictly below the x-axis, and the second region, A2, which is strictly above the x-axis. Here's A2. And so the definite integral, that we computed, is just the stuff above the x-axis minus the stuff below the x-axis. So the area above minus the area below. And that turned out to be 2/3. All right, and I will see you in the next video.